Right. Good morning to all of our attendees. Afternoon Europe time. My name is Leniker Palacios. I'm product manager at GERS USA. I'm pleased to welcome you to our webinar on grid code compliance. Thanks for joining us. So I invite you to leave us any questions you may have in the section or contact me by email, which is indicated in this slide, lpalacios@gersusa.com. I also invite you to contact to our developers team, which is available to support you in anything related to NIPLAN. First of all, I would like to give a brief introduction about our company. GERS is an electrical engineering consulting group founded in 1981. We have more than 40 years of experience providing electrical engineering consulting services and carry out projects in more than 45 countries. Our services line include power system studies, field services, representations such as NIPLAN, which is a software highly used in more than 110 countries. We have more than 500 active customers, and the solutions are related to the transmission, system, generation, oil and gas industries planning and operation. The content of this presentation is split in 6 main topics. First of all, we are going to present a brief introduction. We are going to talk about grid code references, power system studies, grid code requirements like the fault right-through, grid management, reactive power control, active power control, some simulation cases, and finally some conclusions. Starting with the brief introduction, let me talk about something that I called about some considerations. And those considerations are related to something, the framework involved on the power systems evolution. And that is indicated here on the first part. Power systems are currently experiencing a fundamental evolution process. That is illustrated here since we are having a transformation of the electrical networks with new penetration of renewable energy sources. Most of them are interfaced to the grid through power electronics. However, some of them, like the sun and the wind, are variable resources. Another issue is that related to the power electronics, we are getting here some challenges like the low zero high inertia conditions, fast and adjacent dynamics. However, for the future, we can enable many opportunities. For example, new distributed generation schemes. The environment impact would be improved. We are getting some converter dominated systems. And for that, we have to enable some key enablers. Proper designs, operation, and control of the power converters. These key enablers need to address different challenges. And one of the main intention initially is to detect what are the challenges. For example, this research is very interesting since this research is presenting here a ranking about different issues due to the variable renewable energies. And on the first part, we can find how the decrease of the inertia is providing different requirements on the grid code modifications since the control systems should be able to support this issue. Another context that we have here is the transient stability margins, since we have to provide different architectures on control systems for the operation of these kind of resources. I also have here in the sixth position the fault right-through capabilities, excess of reactive power, voltage depth induced frequency depth, and another kind of issues that we have to attack due to the variable renewables energy penetrations. This research was performed using some surveys for some TSO, transmission systems operators. And based on that, we are able to open the specifications on grid to consider different affectations on the high penetration of renewable energy sources. Let's talk about that. Let's talk about some grid code references. And one of that is the meaning of the grid code. And what we can see here is that we have different types of grid codes. We have connection codes, we have operating codes, planning codes, and market codes. In general, the electrical power needs of all customers must be reliable. Voltage or frequency must be maintained within set limits, and we have to avoid damaging of the equipment. The system must be able to recover quickly from any system disturbance. And for that, we are opening different set of rules for power systems operation and the energy market operation. This is the purpose for having grid codes in different countries. And in general, they offer different advantages. For example, they enable network operators, generators, suppliers, and customers to function more effectively across the market. They ensure operational stability and security of supply and contributes of well-functioning in wholesale markets. And finally, it is very convenient to mention that the grid code doesn't mean an energy policy. They are related, but they are not the same. In some cases, the stakeholders shall consider the different policies to create the grid code. I have here a reference. I've been illustrating here different references that I am using for this presentation. Some of them are from HIRENA. And we can see how the grid connection codes are used for variable renewables energy penetrations into the grids. And they have considered different stakeholders, technologies, and the evolution of the power systems, as I meant before. However, we can see how the operational conditions in different countries change. In different countries, they change. Why? Because there are different penetrations or renewable sources. There are different architectures. There are different policies, and there are different stakeholders that will modify the specification of the grid codes. For that, I am presenting here some examples. And we can see how for the US, the North American Electric Reliability Corporation, as known as NERC standards, provide different specifications, like the PRC 024, that is related to the frequency and voltage protection settings for the regeneration sources. And also we are having here the P2800.1 that is providing the different specifications for procedures or inverter-based resorts that is going to be connected to the transmission system operators. In the European side, we are having here also another specification. And that is, for example, the European Association for Cooperation of Transmission System Operators that is specifying some regional codes. But also we can see how the network code and requirements for generation, for example, 2016, and for the network code, we can see for distribution code of 2016 and high voltage in DC systems too. They are providing different specification of the frameworks to be considered on the limits, operation limits, and the procedures to connect any new variable renewable energy. Another example we have in India and China, the specification on the grid codes. But also, if I look for different applications, I will find a grid code compliance requirement per country. Each country will have their own rules, and the rules will consider the different specifications, the variable limits, and for sure, what is the best procedure to keep all the performance properly according to the requirements for the stakeholders. Finally, I would like to present here some international standards highly used. For example, IEEE 1547 is providing the specification of connection of DERs into the distribution systems. And the IEC 61400 is providing specification for wind generation, having the opportunity to provide assessment for the connection of these kind of systems. In some cases, the international standards are used for the specification of grid codes. This presentation is going to be oriented in the technical requirements. And we can see how the technical requirements will change depending on the penetration of the variable renewable energies. For example, as a minimum requirement on the electrical systems, we have here the protection, the power quality, the power reduction during the over frequency. And we can see how if we increase the penetration, for example, in higher variable renewable energy resources, we can see that we have a specification about low voltage right through, including current contributions. And we have to validate properly the simulation models. And here, if we have power systems composed mainly by variable renewable energies, we can see another specifications, like the standalone frequency and voltage controls, the integration of frequency and voltage control schemes. They open different requirements for the network planning and operation. Many requirements means the investigation of the power system. They should consider capabilities of the available generator systems and if they can contribute on the stability of the systems once the variable renewable energy resource is connected. The required simulations should consider power flow studies to research about the reactive power needed to support the capabilities of the other generators. They need to identify different capabilities of the existing products or the existing technologies to validate the potential capabilities and lower cost. Static and dynamic simulations are required to validate the protection settings and low voltage right-through requirements. This list also considers some parameters to be included in the grid code compliance specifications. I am illustrating here, for example, a list of studies required on the and recommended to get different parameters specification on the grid code. So we have here different references that offers the state of the art in this kind of requirements. For example, reactive power capability for voltage control, voltage and frequency operation ranges are required on power system simulations using load flow simulations. However, in some cases, like the frequency support and the fault behaviors, request another kind of simulations, like dynamic simulations, that are able to support the behavior of the network during a specific fault. Power quality, active power gradient limitations, the simulation models, and as I mentioned before, the active power management, communication, and protections. There are different technical requirements, and there are different power system studies that allows to follow the technical requirements for the specification of the grid code compliance. Let's talk something about that. Let's talk about the power system studies required on the grid code compliance. And let's start first of all with the thermal and transient stability models for the inverter-based resources. And I have here an initial reference. This reference is more oriented to provide genetic models. And the genetic models can be useful in some specific case where the genetic model is acceptable. And that is a specification that shall be considered on the grid code compliance. And it will depend if the model is providing accurate results on the dynamic response of the real system. And also it opens different opportunities to create the model if the information from the manufacturers is not available. Another tool that, or another opportunity that having genetic models is to provide different libraries, because including the genetic models into the software directly will allow to avoid that the user defined model is created. I mean, in this case, the modeling will be faster since the simulation is using a genetic model. These genetic models are included in this case using NIPLAN for the validation of the system's performance using dynamic simulation. However, let's talk about different analyses that we have to consider on the power system studies. The other one is about the thermal analysis. The thermal analysis considers steady state or power flow conditions and short circuit simulations. And I'm illustrating here over a distribution network how the power system simulation allowed to validate the impact or not for the topologies, for the loadings, and for sure for the connection request of any kind of device. In this conference, we are orienting the simulations for variable renewable energies. And we can see how the power flow simulations allows to validate if the system is able to support new generation. And the specifications, for example, in some cases for distribution systems, we are also opening new requirements on simulations to detect the maximum load capabilities, like the hosting capacity for locations, but it is for distribution systems. In transmission systems, we have another kind of requirements that are oriented on the grid code compliance, also on dynamic simulations performance that I will illustrate later. In this case, also, it is convenient to mention here that the short circuit analysis will contribute to check the ratio of the change on the short circuit levels. And we can see how we can compare a base case with a new study case. The grid code requirements means what would be the maximum allowable change or delta that the new connection request should accept or not. Let's talk again about the transient stability, since this is one of the main challenges speaking about the connection request or the new requirements on the grid code compliance for the specification of variable renewable energies. Again, I am presenting here the genetic models, but what happens if the genetic model is not acceptable? We have to create the model and we have to include the specifications per manufacturer to validate if the control systems is able to support or not the different requirements on the grid code compliance. This is a summary of different manufacturers and references that we have modeled in GERS for validation of the simulation models and to validate the system impact study and the thermal conditions for the power system studies that we have been performing. For example, in Florida, we have more than 100 projects developed for the planning of the operation of the transmission system operator. Each project will need to create the specific model for the variable renewable energy and validate the impact. Some issues that we have considered, or maybe, or better, some concerns that we can consider during the simulations is about the synchronization of the model. And in some cases, we have to validate if the simulation model is acceptable or not for the grid code compliance. For example, field test and model validations using the specification of mod 026 or mod 027, which are related mostly for generator excitation systems and governors. I mean, they are more oriented to typical generation. And we can see how the system performance should be closed to the simulation. And if we are able to validate the system, the real behavior, and the behavior during the simulation, we are having the tuning of the proper validation from the simulation to the grid code compliance. However, we can see also another concern here, for example, that the user-defined model doesn't meet the specification of the PRC 024, which is related again to the setting criteria on the protections for keeping the operation of the system during a specific fault. Another kind of concerns that I am listing here, the injection of more reactive power than the capacity of the plant. We have here another concept that we have a more active power during a specific fault, momentary cessation to the fault, specific protection, high oscillations, and this is also one of the concerns that we can find during the simulation, and that is the active power increases after the fault. And those results can get values greater than the capacity of the plant. Based on that, it is convenient to check what are some grid code requirements that we have to consider during the simulations. Let's talk about some of them. Since we have different challenges on the verification of grid code compliance, we have to create proper models. And the proper models should able to provide different solutions, even to the customer side and even on the transmission system operation side. For example, the plant owners, they will need to demonstrate the compliance of the model and the connection of the project. But the transmission system operator has to assess the compliance. As an advantage of that is that the grid code compliance can ensure the stable and safe operation of the system. And we have here different requirements typically used on the grid code compliance. The first is the fault right-through. The fault right-through is illustrated here. And we have low or high voltage right-through, which means that the system is able to support the operation of the system even during the fault. And we have here also the reactive current injection during the voltage depth. Another requirement is the reactive power control, and we have different control strategies. How can we modify the set point according to the voltage level, or according to the power, the active power, or according to the reactive power? We have to consider priorities if we would prefer to inject active power or reactive power, depending on the control system. The other one is the active power control. And in this case, we have two ways: the reduction of the active power at the over frequency, or the frequency response at the low frequency. Finally, the grid management. And in that case, we have to consider controlled active power by the grid operator or the power gradient of constraint. Let's talk in more detail about these kind of requirements. For example, there are some reviews of the grid code technical requirements here. This reference is associated to the grid farms, but I would like to mention that in general, the impact of the variable renewable energies interfaced through the converters, the final response is due to the control response of the converter. And in that case, the specification comes from the availability of the technology in the converter to support the different control specifications. For example, for the context in the US, we can see here the specification of the requirements on the fault right-through. And we can see how the generation plant must be able to operate continuously at least in 90% of the rated voltage. Regarding the reactive power control, we can see some requirements depending of the grid code requirements of the country. We are having here a comparison between the different specifications. In this case, this comparison is for the fault right-through. And we can see this is the curve used for the US, but we have here also the specifications for the context in Germany, for the context in Italy, and for the context, for example, in Hydro-Quebec. And one question is why they are different. Why the grid code requirements are not the same for all the countries? And the answer is related to the comments that I presented before. The network topologies and architectures are different. The stakeholders are different. The energy policies are different, and many other topics that affect the specifications on the grid code requirements. I have here different control systems, for example, reactive power control, where the power factor is a function of the active power. Reactive power control, where the reactive power is a function of the voltage, which is illustrated here in this graphic from NIPLAN, where basically this behavior is typically used also in static bar compensators, but this is for transmission systems. And these kind of technologies are mainly used to support reactive power injection. And if we are speaking about variable renewable resources to generate active and reactive power, we are having here the prioritization between the active power and the reactive power. And we have here also the specification of the active power limitations, where the active power could be a function of the voltage. Again, this reference is very good since it's showing a comparison between different requirements on the active power control in different countries. And the difference of that is due to different stakeholder specification according to the specific operation and planning codes that we have per country. How to simulate? Can we create the model to validate the grid code compliance? The first step is to check if the grid genetic molds are acceptable. If the genetic model is acceptable, we can check if the dynamic response can meet the specifications on location or different type of faults. For example, dynamic simulations can be performed in symmetrical components or can be performed in the phase framework, and depending on the type of fault, because for example, asymmetrical faults can be useful. The framework in the phase framework is useful to validate the performance of low voltage right through in asymmetrical faults. And in symmetrical faults, the symmetrical components for this kind of simulation would be useful. In some specific cases, the electromagnetic transient simulation are also required when the simulation in RMS is not enough to validate the oscillation of the frequency, and we have to check in the time domain of the instantaneous values what is the performance of the control systems, because in some cases the EMT simulations can present some behaviors that the simulation in RMS are not enough. Another requirement is the possibility to connect the control system to the external applications. And based on that, different architectures, in this case, NIPLAN on the cloud, is allowing the connection with external tools. And that is able to support the real behavior with the simulation model. Another requirement is to define a new kind of disturbance of the power system. Before, we were able to validate the system performance during a specific short circuit, the system performance if any contingency occurs. But today, speaking about fault right through, a new kind of disturbance has to be defined. And that definition is called the low voltage right through event that we are going to check later. And the software should be able to provide a tool to create this kind of event. If the genetic model is not acceptable, we have to create a user-defined control. SINDEF is the language that NIPLAN is able to support to create this kind of user-defined models, or using function blocks to connect the transfer functions. Finally, the variables initialization, and this is very important to take into account these requirements, because in big systems, the variables initialization could need automatic variable initialization to having an optimization of the time processing. In some cases, the parallel computing, in this case with the cloud architecture, that can support fastest simulation than even the real life. In some cases, the grid code compliance shall perform simulations in the time processing where the time is lower than the real time that any event can occur. And I will illustrate that later. The dynamic security assessment is basically when we are able to perform a dynamic simulation during a specific period of time, what are the variables with limits violations. For example, maximum currents, minimum voltage, maximum angles. Typically, we are able to monitor these variables: voltage, current and power, generator, and voltage angles. And for that, we have to perform an automatic validations of different scenarios at the same time. Let's present that using some simulation cases. One example is to create the model of one kind of the inverters. And I will present this example of the grid forming inverters because this is an emerging technology. And to date, there is no standardization available. The required simulation of this kind of technologies may not be available in libraries of system analysis tools. And in that case, we will need to create user-defined models. And to create a user-defined models, we need tools for easier definitions of the system variable states, the differential equations, and the algebraic equations. SynDef is the symbolic definition, and this is the way to define dynamic models in NIPLAN. It's a test file with extension is the own extension SynDef, and allows to create user-defined models easily, and is able to share in a password protected feature. For example, the grid forming inverter that we are going to model here is based in the virtual synchronous machine specification. This is a virtual synchronous machine control. And what we have here is the definition of differential equations. We have a test-based file, which is able to create the specific model for the differential equations and for the algebraic equations. These equations can be included here in the user-defined model. To illustrate that, let's present here the IEEE 39 notes. And this application case is presenting here different conventional sources from the synchronous machines. How to validate the impact if we replace the synchronous machine per inverter-based resources with grid forming controls. So we have here the different specifications of application of NIPLAN. The network modeling can be oriented for per specification of the grid code compliance and per acceptation of the different standards. For example, the standard can be also specific for even for the way to illustrate the connection of the elements, and we can even consider the different standards even for the symbols representation. And in this case, we can see how we can change from one standard to other one easily. The different power system studies required on the grid code compliance are accessible through using a list of different available models, like the power flow that is able to perform thermal analysis to validate conditions during the steady state conditions. And in this case, we will be able to validate if the system would be able to support or not the carrying condition of the system. Overloadings, under voltage or over voltage can be detected using steady state simulation with the power flow solution. The short circuit simulation is able to provide the approach to validate if the short circuit ratio will be affected or not for specific projects. Let's talk about the dynamic simulation for this example. And as we can see, the IEEE 39 bus is presenting here that I have here. Initially, I will create the model with the synchronous machine generator. And I will validate the impact of the control system. Let's open here because the way to define dynamic controls in the context of synchronous machines, we have the way to define the voltage regulator or the governor or the power system stabilizer. And we can see how the framework is able to provide here typical functions according to the standards, in this case, to support the control system. In the context of the synchronous generators, we can see how the different possibilities in the control system are implemented as predefined models. And to date, since this kind of generation is being used since several years ago, we can find that most of the control strategies are implemented as predefined models. That applies for generation, that applies for regulators, for governors, and power system stabilizers, since in this case, we are also considering genetic models. So to check the system performance during the dynamic conditions, we can check, for example, that we can run the simulations using the symmetrical components. We are going to perform the simulation in the time of 10 seconds, and we are going to define an event. For example, we can define short circuits, or we can define a opening of the system, or we can define a low voltage right through, which is going to be illustrated later. In this response, for example, we would like to check the response of the frequency and the voltage during the event. We can see how the impact having generation system based on synchronous generation, the event we are having here, the behavior of the frequency that has been affected by the event, by the disturbance. And we can see that the frequency can, the control system can support the frequency stabilization, and the time that the frequency stabilization will take is part of the specification of the grid codes. And we can see what is the behavior per specific locations or per specific synchronous generators that we have on the system. That means that we need easier tools to validate the impact per location, per generator, or per different elements that we have, like the transmission lines or like the transformers. Well, so in the context of the grid forming inverters models, so we have here that the way to define the inverter-based resource with non-standardized model, we need to define a user-defined model. And in this case, the user-defined model can be processed with the SIMDEF editor, which allows to create the variables, the initialization, and the equations, as I explained before. This is a test-based file, since we are able to write directly on the test-based file, and it allows to create the model in an easier way. For real, the way to create user-defined models using the SIMDEF allows to create models in order to validate the impact of the user-defined models. In this case, for example, I will change the operation. And what I'm going to do is to change the operational state. Instead of having here the connection of the generator, I will use the operation of the inverter-based resource. We can see how I can change the operating mode. And in this case, for the same event, I will consider the participation of the grid forming inverters. And what we can see is a very, very interesting scenario. Let's proceed again to the simulations with the synchronous machines. So we can see how NIPLAN allows to run the different steady state conditions, the different conditions of scenarios at the same time on the same database on the same project. And we can see how the simulation of the grid forming inverters are providing here an equivalent behavior but a fastest response. And this response is being validated depending on the requirements and the time that the frequency response, and if I show here the voltage response, we can see how the performance using this kind of models that are using power electronics can support fastest implementations, but it will depend on the model. In this case, we are having the comparison between the generation with synchronous generators and the generator with inverters using grid forming model. Well, let's talk about the low voltage ride-through events. In this case, I am showing here the example for the specification of the impact of the connection of the specific resource. In this case, we can consider different kind of resources. And what we have here is a framework that is related to the specification of the active control, reactive control, and what are the limitations on the current or the limitation of the active power. Specific control systems can be defined and the connection framework if they are accessible through the genetic models, or again, if we have to consider user-defined models. The specification per symbol, again, we can use ANSI standard or IEC standard, depending on the context where we have on the countries. How to proceed? Again, we can define a time simulation, and here, let's proceed here because the architecture should be able to implement here the events parallelization, and that is useful in big networks to provide a lowest time during the simulation. In this case, the event, let me show you here that we can define an event on the point of common coupling. We can define here an event not for the short circuit, not for the three-phase short circuit. In this case, we can define low voltage ride-through or over voltage ride-through events. In this case, this event can be defined here, and we can set the different positions or what is the magnitude of the voltage for specific times. Let me show you that, and we are going to plot here the voltage in terminals and the active power and the the control signals. Let's present here how we get the low voltage right through. And in that case, this specification, let me talk again here about the event. So we have defined here an event where in 1 second, the voltage is going down to 0. And in 1.25 seconds, the voltage begins to increase. This is the system performance in voltage terminals. This is the system performance for the active power injection and the reactive power injection. The low voltage ride-through specification here should meet the specification on the grid code compliance, and we are able to supply or to support these validations if they are inside the limits on the grid code requirements. Again, the control signals can be also specified during the dynamic simulation. Finally, let's talk about the control modes available to support the active and reactive power controls. And the active and reactive power controls can be performed on the specification on the model for distributed generators. And we can see how the different specifications from different control curves, depending on the specification of active or reactive power support, we can define here the curves. And we can see how we can create, for example, the control systems when we have the power factor as a function of the active power. And we can see how, depending on the active power injection, we can modify or not the point of operation in the reactive power system, capacitive or inductive side. For the same generator, we can see how is the impact if instead of having that kind of control, we are able to get the control of the power factor as a function of the voltage. In that case, the curve should be different, and that is able to support the reactive power or the reactive power injection of the reactive power consumption, in this case, depending on the voltage level. Finally, regarding the active power management, we can see the model to get to consider here. Sorry, this is the reactive power control associated mainly to the typical behavior of the static back compensators. And basically that is able to provide provide the reactive power injection or consumption depending on the voltage level. If we have low voltage, we need to increase the reactive power injection. If we have high voltage, we need to reduce the reactive power injection. If we perform the simulation for the same conditions, we can see that the point of operation is different. For the same for the same active power injection, we can see that the reactive power has been affected, and in this case, the reactive power having the control of the voltage as a function of the reactive power as a function of the voltage can create more requirements on the reactive power injection. The question is, are these results acceptable for the grid code compliance? So in this case, what we will need to check is the monitoring of the results and the monitoring of the limits specifications per country. And for sure, if these specifications, for example, if we are speaking about the IEEE 1547, the IEEE 1547 is able to specify the operation points, and if the reactive power support is higher than the specification of the IEEE 1547, we are not able to accept the connection of DER in that point specifically. Well, so they are the different applications. In this case, for example, we have seen how the system performance has been affected by the model of the grid forming inverters. That was the first application case. And we can see that the countries, as I discussed before, the time of the time that the frequency control will take, the time specification is can be used as a reference depending on the country. For example, in some contests, if the frequency is too low, for sure that we know that the system cannot support that for big time periods. Typically, some countries are able to support the frequency control in a time of 20 seconds in some countries. In other countries, 10 seconds are allowed as a maximum control. But again, that would depend on the grid code requirements per country. Also, we can see how the global dynamic behavior improved when we use the grid forming converter, and the local transients in this case they didn't change. We can see how this local transient here, that is the transient of the location of the synchronous machine, it was more or less related to the simulation from the synchronous machine. The other simulation that I presented here is the specification of specific low voltage ride-through profiles. And in this case, what we did was to define a low voltage ride-through event, and we have validated the system performance during the dynamic simulation. Finally, let's present here the application of the parallel computing, because in this case, we can see how the bus bar on the whole European transmission system, in this case, the ENSO model, that is, it has around 21,000 nodes. The simulation is, in this case, taking 35 seconds for an event that in the real life will take 50 seconds. I mean, the simulation is faster than the real life. And in that case, the question is, how can we support the grid code compliance with the real-time simulation and if we can accept or not the system behavior for specific operational states or specific events on the systems. Finally, on the distribution side, we can consider the connection request in medium or low voltage. And the connection request can have different rules that can be automated. And those rules, in this case, can be accessible anywhere the user can define or can ask for the permission to connect variable renewable energy or for different technologies like the electrical vehicles too. And we will be able to validate if the connection is acceptable or not. And the rules that we implement per country are according to the grid code requirements for the distribution systems in this case. But also, I would like to mention here, if the transmission systems is modeled in other software and the grid code requirements means that we have to consider the system performance on the transmission system too, it is convenient to mention that NIPLAN can import PSSC that is highly used in the US. NIPLAN can import the common information model, and the common information model means that all the software that can demonstrate conformity with the model in the transmission system operators, we will be able to import database from any other software that is able to provide that. So the message is that we can't worry if the database is not in NEPLAN because we can import and we can manage the information directly on the cloud, and we can implement connection requests automatically using the rules from the grid code compliance. Well, so I will present here 4 conclusions. The first conclusion is that the power systems are currently experiencing the fundamental evolution process, that it was the first slide that I presented here. However, grid code compliance is essential to ensure the operational stability and security. The main driver of that transition is the progressive integration of renewable sources. The second conclusion is that the stability and reliability, flexibility aspect, they are different concerns on the grid code requirements. We need power system studies to validate future, and it is essential part. We need experience to create models, and we need experience to validate power system studies on the connection request. Grid code compliance requires dynamic simulations, and as I have been explaining here, if the positive sequencing modeling approach is useful in symmetrical faults, and the three-phase reference frame is useful for asymmetrical faults, when also the grid code requirement is orienting the low voltage right-through with asymmetrical faults. Finally, demonstration of grid code compliance and achieving grid code connection is performed accurately by the advanced NEPLAN dynamic simulator that is used by the system operators in electric utilities around the world for power system analysis. Our solutions is GERS, NEPLAN team, since we are able to perform the power system studies directly, and we are able to integrate the simulation model directly on the SCADA or MEMS system that is able to support in real time the grid code compliance. We present different trainings in power system studies and smart grid applications using real technologies. As I am showing here in the background, in the laboratory, we have real technologies in IEDs, generation system, and loads. We can design the controls and protection schemes and implement them, testing and commissioning of the different technologies, and we can get the protection settings. So I invite you to follow us on the NIPLAN applications, since we are able to create different applications and customized applications for the interaction of the network database with different applications like the GIS, like the SCADA system, like the smart grid applications, protection device management system, and asset management systems. So exactly, I have here 55 seconds, 55 minutes. So the time is enough to attend some questions. Again, thank you very much for attending this presentation. My email is lpalacios@gersusa.com. I can support you on the power system studies requirements, on the real-time integrations, and the licensing scheme with NIPLAN directly. I invite you to follow us in the social media, LinkedIn, Facebook, and YouTube. We use to share there our videos recording on the webinar. But also, I invite you to subscribe your account in our GERS Academy platform. In our GERS Academy platform, we are uploading different tutorials and different trainings in protection systems, and all the webinars can be accessible by free here. Thank you very much again for your attending, and let me check if you have any questions. Please do not hesitate to contact me. Well, I will check here some questions. Please send the recording. Absolutely. I will invite. I will share the presentation, and you can subscribe to our GERS Academy platform, and you will find there the recording of this webinar and previous recording for different topics that we have been presenting on the power system planning and the power systems operation. Can you share the presentation? Absolutely, absolutely. I will share to the subscribed attendees this slide regarding to the grid code compliance. Well, I don't know if there is any other question. Thank you very much, sir, for your presentation. It was amazing. Thank you very much, Mr. Ansher, for your comment. I hope you found this presentation useful. So this webinar is for 1 hour presentation, but the content of the critical requirements around the world is very extensive. So I think the trainings on the power system studies requirements required for the grid code compliance are very big, and the implementation of this kind of requirements or this kind of simulations need better trainings. So I am open to support you by remote connection, or I am able to visit if you will have specific issues to be solved using dynamic simulations or using cloud computing. Awesome. Since we don't have any questions, I have here around 11 in the morning in the US. And if I invite you to write me for any other requirement, thank you very much again for attending this presentation. And I hope you found this presentation useful. Take care and see you later.